Hi everyone. So this week we're going to continue with multigrid methods. That's basically the topic that we've laid the groundwork for last week, when we covered smoothers and kept repeating the fact that smoothers reduce the high frequency errors first. And high frequency depends on what grid you're on. So a high frequency is anything basically where there's oscillations which are on the size of the mesh width that you're currently on, which means that if you coarsen the mesh, what was previously a low frequency error might turn into a high frequency error. And we're going to use this by making a hierarchy of grids and applying smoothers always to reduce the errors on that level. So the first part here is grid-based methods. I think that for most of you it's probably clear where the grid is coming into this, but I wanted to repeat, or for those who haven't seen it, show you for the first time finite element methods. In the tutorials you'll have had finite differences, which is a different way of discretizing partial differential equations onto a grid. There's also other methods that we won't go into at all. In the end, all of them take a partial differential operator and they turn it into a matrix vector system. So that's why we're spending so much time on trying to solve efficiently matrix vector systems. So as an example, we're going to use the Poisson equation in 1D. The Poisson equation is a pretty simple equation, so it's just a double derivative on the function that you're looking for, which is u here. Then we've got some right-hand side vector f, and we've got boundary conditions here, so at 0 and at 1, so at the interval endpoints, we assume that the solution will be 0. You don't necessarily need to set the solution 0 at the endpoints. You can make a lot of other choices, but you do have to set something at the boundary because otherwise your problem isn't well defined. So you can see with the double derivative that if you had a constant solution and you didn't set the solution at any point, then any constant would remain a solution. So that's why we need to have boundary conditions. So we're going to discretize this on a mesh of n equidistant points, which will give us a linear system to solve. The finite differences was covered by the tutorial. That's one way of doing this. So let's have a look at a different way of doing this. So finite elements rely on a weak form of the partial differential equation. I'll show you in a second on the whiteboard how you actually derive this weak form, but for now the point of doing this is that it allows for weak solutions, so you can reduce the regularity assumptions. On the previous slide we saw a double derivative and u needed to be continuously differentiable 2 times. On this slide we see that our solution u only has a single derivative on it, and there's also an integral now, which means that it only needs to be weakly differentiable once. Weakly differentiable here means that the integral that we are looking at here needs to exist for all functions v. So let's derive the weak form then. First, let's just remember what equation we're solving. So this is the equation that we're solving on the interval 0, 1. And we've chosen Dirichlet boundary conditions, so we've just chosen a solution which is 0 at the left and right endpoints of this interval. So we know that it's 0 here, the solution, and now we want to find it. It's going to look something like this in this case. So to do finite elements, what we need is the weak form, as I said before. And I actually already showed you the weak form, but now let's see why it looks that way. Okay, so we start with this equation. And now we multiply both sides with some function v. Okay, so where does this function v come from? We'll discuss that later. Also, why are we doing this? We'll discuss that later. For now, we just multiply both sides with a function v. And then we integrate. So now we're going to integrate from 0 onto the interval 0, 1. The x there as well. And now we look at this term and we partially do partial integration. So then we get a sign change. We now only have a single derivative on u, and we've shifted the other derivative onto v. And then what we also would get is boundary terms. So what we would get is terms like this. But since we've chosen Dirichlet boundary conditions, this term is 0. And then we have the right-hand side, which just remains. We don't do anything with this. Okay, and now we've already got the weak form as it was also on the slides. And our next step to actually solving this equation would be to choose some ansatz with which we can solve u. So let's assume that u can be written using some basis that's not specified for now. So then it's some coefficients, so these are just numbers, times some basis functions. And if we assume that our solution has this form, then we can insert that into this equation, and we can start to solve. So that's what we'll do in a second. So now that we've seen the weak form, and we've also already seen how to discretize it, so now we know what this basis bi is, and we know that we can write our function approximately as a sum of these basis functions times some coefficients. We've reduced our problem successfully, and we now just need to solve a linear system for these coefficients ui. So let's have a look at these grids and see what I meant by multigrid. So this should be pretty clear. I just wanted to clarify it again. So if we have n grid points, we have a mesh width, actually it's 1 over n minus 1, there's a typo here. Then we can take our interval 0, 1, and we can divide it up into subintervals. And since they're equidistant points here, each of the grid points will just be I times h. Okay, so we can have a look at that. Don't know what happened here. Give me a second. Okay, now we've got that. So if we take a pretty coarse mesh, then we would get something like these orange points here. So there's 5 points. They're at a distance of 0.25 from each other. That's our h. And the finer grid, you can see, has exactly points at half in between, so it has a mesh width of 0.125, and if we refined again, then we would get another point here, another point here, another point here, and so on. So here's that one. Okay, so that's what we're going to do. We're going to build just such a hierarchy of grids so that we end up with a bunch of nested grids. So always the points of the coarse grid are also going to exist on the fine grid, but we get additional points at the half points of that interval. And since I'm always discarding the two end points, 0 and 1, that's why these numbers are always going to not correspond directly to halving, but the interior grid points are halved. Okay, and before I just said, okay, so we have some basis of our vector space, and it was completely abstract. Let's look at a really simple example. This is a really commonly used basis for finite elements, but of course there's others. You can use higher polynomial degrees. This is a linear one. You can also use lower ones in some situations, although not for the problem that we've just been looking at. And this is essentially just hat functions. Let's have a look at what they look like, since the formula is not perhaps directly clear. So as you can see, they're called hat functions because they look like little hats. The blue one here, for example, is the first one, which is centered at the node 0.25 here, and then it's 0 at every other node. So the first part of this is the slope here, and the second part is the slope going down, and then it's 0 everywhere else. And we can do that for all of our interior nodes. So in this case, there's 3 of them. If we had a larger n, then there would be more than 3 of them. And in total, we get a basis which is piecewise linear. So we are searching for solutions which are piecewise linear and can be written as a sum of these basis functions. These basis functions are then typically called shape or ansatz functions, depending on what book you look into. And they build a vector space, as I've said before, or a function space, V. So the span of them is some function space. In this case, it's the function space of piecewise linears. So if you choose a different form of the basis, but it still spans the same space, then you have essentially the same finite element method. You've just chosen to implement it slightly differently. But you can also choose a different function space. So you could choose, for example, piecewise quadratics. That's not quite as common as using piecewise linears. But then your function space V is different. So now, how to get the matrix vector form? Well, we insert our basis representation of the function into the weak formulation. And then our problem becomes finding the n coefficients such that the following equation holds for all test functions V. So how do we solve for all test functions V? They're still abstract. How do we get all the functions from our function space V? That's the open question here. And the answer is quite simple. We just choose the V's to be each and every basis function of the space V. And since any function in the space V can be written as a linear combination of its basis functions, such as the definition of what a basis function is, we know that our equation must then hold for all V in the function space. So if we insert that into the equation, then we've just rewritten it in this form. So this is still exactly the same equation as on the previous slide, only now we've replaced the V's with BJ's. And now there's nothing really that's unknown here except for our coefficients ui. So we know our basis functions, and we know our right-hand side. So now all that remains is to solve this, right? Essentially what we now have is a system of equations of unknowns. Here the functions V, I've referred to them that way before, I think. They're referred to as test functions, and they're referred to as test functions simply because we basically test whether the equation holds for each of them. And that gives us n equations for n unknowns, which we can then solve. So in total, we get this linear system, AU equals F, and the entries of the matrix A are just given by the so-called bilinear form. So that's the integral from 0 to 1 over the derivative of the first basis function times the derivatives of the second basis functions. That is our matrix A. It's also often called a stiffness matrix. It's called a stiffness matrix for historical reasons, because some of the first, at least, equations for which finite elements were used were elasticity equations, and in that case, the entries here end up actually being the stiffnesses of the material. And then when finite elements became more widely known and more widely used, the name just kind of stuck, as far as I know. You can also refer to it as a system matrix. Some people do that. But yeah, stiffness matrix works as long as you don't get confused. There's no stiffnesses in here unless you're doing elasticity. Okay, and then you've got your right-hand side where you just tested your right-hand side with a basis function bj, and then that gives you fj. Okay, so now we have a system of linear equations. That's exactly what we wanted, and it's corresponding to a grid, right? So these bj are always nodal basis functions. They correspond to one node on your equidistant grid. And we can build a hierarchy of grids, as we saw before, that are nested. So each of the values on the coarse grid also exists on the fine grid. And so now we can try to solve our equations with smoothers on each of those grids. Okay, so actually we're not moving on to multigrid now. There was one more slide that I forgot about, so let's look at that first. How do we actually compute the entries fj? Well, I've already told you that we're basically just multiplying them with the basis function bj, so you can see them in some sense as a weighted average, and then we have to compute this integral. And we generally compute this integral with numerical integration. So we turn it into a sum of function evaluations times weights. And in this case, since we know the form of our basis functions and they're just piecewise linears, we can divide this up into the two sections that our basis functions had and then just integrate in the regions where they're non-zero. So that's just a way of computing this more efficiently. You should definitely do this if you're solving this in practice, but of course it's just an identity here, so this is just that integral. It's just easier to solve numerically if you divide it up like this. Most integration methods won't be very good at integrating functions with a discontinuity, and since we already know that our basis function has a discontinuity, we can divide it up into those two integrals. Okay. And then the second part, of course, is the matrix A. For that, we'll move briefly to the whiteboard just to solve what the matrix A looks like in the case of the Poisson equation. So the first part here is just our bilinear form, which also already depends on the Poisson equation. For a different partial differential equation, this would look different. And now, in this case, it's very easy to evaluate, so let's evaluate it. Okay, so now let's compute the matrix entries. So this is the matrix that we want to compute, and we already know the form that BI has. So this was just 1 over h x minus xi minus 1 in xi minus 1 to xi, 1 over h xi plus 1 minus x in xi plus 1, and 0 otherwise. So that was our basis functions, and now it's already quite easy to see that if these intervals at which the basis functions is non-zero never coincide for I and j, then aij will be 0. So that basically tells us aij is equal to 0 if I is not equal to j, if I is not equal to j minus 1 or j plus 1. So those are the only situations in which we get a non-zero answer. Okay, so let's assume that we want to look at a I. So the case where these are identical, then we can again just write this down. So we have the integral 0, 1, then we have the derivative of bi, and the derivative here of a linear function is pretty easy to compute. So let's divide this up into our two intervals. So starting with xi minus 1 to xi, then we have 1 over h, and well, x derived is just 1, so this is just 1 over h. And then since it was bi times bi, we have 1 over h dx. Okay, so this part will just give us 1 over h, because we're going to get an h factor in from the integral itself here. And then we have the second part, so it's xi to xi plus 1, and in this case we're going to get a minus sign, so we get minus 1 over h, and then we do the second one, also minus dx, and then this term again gives us a 1 over h, and in total aii is now 2 over h. Okay, and then we can do exactly the same thing also for the case where I is equal to j minus 1, only then one of these intervals is going to be 0 for one of the basis functions, and we just essentially end up with this minus 1 over h. So let's do that for one of them, but not for both. They're symmetric. Aij is equal to, okay, so now this is, let's say it's I minus 1. So xi minus 1 to xi. So then we get 1 over h for xi, and for I minus 1, we now in this section, so we get a minus 1 over h dx, and again, this term will just be equal to minus 1 over h, because we get an h in from the integral, and then this part, so integral from xi plus 1, well, for the basis function bi minus 1, well, it's 0 in that interval. So we get a 1 over h from bi, but we get a 0 here. So that turns to 0. And then the same thing happens the other way around for I plus 1. And that's the form of the matrix. So to finish up this part of this of the course, some notes on finite elements. I hope that you've seen finite elements before in other courses, or will see them again in other courses, because they're quite commonly used numerical methods, and they're very, very flexible. So here I've showed you only a very simple equation, and I've only shown you a very simple piecewise linear method, but of course you're not restricted to that at all. So the first thing that you could do is you could say, oh, why are we choosing test functions which are from the same space as our ansatz functions? And the answer is you don't have to. When you choose a different space for the test functions, it's called the Petrov-Galerkin method, and you actually need to do that for a lot of problems. It's not always possible to choose these functions from the same space. When they're chosen identically, as we have here, then it's called the Ritz-Galerkin method, but I think that's not particularly relevant. They're often just called Galerkin methods. And the PDE obviously does not have to be the Poisson equation, it does not have to be in 1D, and the grid does not have to be an equidistant grid. So we can follow exactly the same procedure for more general second order PDEs, such as something in this form. So here you've got L, which is some arbitrary partial differential operator. And then you can always derive the weak form in exactly the way I showed you by doing this partial integration. And if this contains terms which don't have a double derivative on them, then you end up with an asymmetric formulation, because then you don't have a second derivative that you can shift. So then you don't have derivative of a basis function times derivative of a basis function, but something like derivative of a basis function times the basis function itself. Okay, but the general procedure remains. So we can look at this in code as well. So for now, let's just choose a really small example. So we've got 5 grid points. 2 of them will be the outer grid points, and if you remember from the first slide on this, then we've chosen to keep the boundary nodes at 0, so we don't need a stiffness matrix entries for them, so we end up with a stiffness matrix with 3 entries as here, and it just contains -1 on the diagonal as we computed, and 2's on the diagonal, -1's on the off diagonals, and then we have to multiply with 1 over h, which in this case is just n-1, and that gives us a stiffness matrix. So of course we can do this for larger n as well, and then we get a larger stiffness matrix and so on. So that's the first part of this. So that's already quite simple. Now computing the right-hand side is not a whole lot more difficult. let's assume that as the right-hand side, we've just been given the function sine of pi x. Then what we need to integrate is just this function f, so that's our function f, times the basis functions, so this is the ith basis function, right? So that's all we have to do. So here we're just using the built-in Python function, which is part of NumPy. No, it's part of SciPy, I think, and it just computes the numerical derivative of the function you give it. So in this case, of our right-hand side multiplied with the basis function I. So we do this for all i's that we have in the interior, and then we attach some zeros to the outside because we already know that at the left and at the right boundary we have 0. And then we can plot our right-hand side, although this doesn't correspond directly to the function here. There's a weighting factor in there. We can see that it has the same general shape as the right-hand side. If we now choose n equals 9, then we get a bit closer to that. And if we chose 17, for example, we'd get even closer. Okay, but there's also a scaling factor in here, as you can see. I don't understand why it's there. Okay, there's a scaling factor in there, as you can see. So the size of these is different. Okay. So let's go back to 9, because we had our stiffness matrix in the end for 9, and they're going to need to match up once we try to solve this. Let's clear off all the plots as well once. Okay, so that's just the plot of the right-hand side for n equals 9. We've got the stiffness matrix for n equals 9 as well. And now we need to solve. And so in this case, with this particular right-hand side that we've chosen, so pi x, sine of pi x, and these boundary conditions, we know the exact solution. So you can just plug that into this equation and see that you get out sine of pi x. So if you derive this twice, then one time you'll get a minus, which will lift away this minus sign, and then you will always get a factor of pi out from each derivative. So it's quite easy to see that this is the correct solution for this. Generally, of course, when you're doing finite elements, you don't know the exact solution. But here we can always compare and see what our error is. Okay, so let's go back to 9. So these are all things that we computed last slides. So the stiffness matrix here is the stiffness matrix as it was computed before. So we know what it looks like. And f here is using the right-hand side function that we also defined before. And then we're just setting our solution u using the solve function that's built into NumPy. And giving it the Dirichlet boundary conditions that we already know. So we're setting it to 0 at 0 and 1. And then we can plot the solution, and we can plot the exact solution. So the exact solution here is the orange one, and in blue you see our approximation. It's already quite good, even though we've only used 9 basis functions right now. If we'd gone with the more coarse model, then we would get this picture. So now you can see that there's fairly large errors on this coarser grid. And if we choose an even finer grid, then our solution is almost indistinguishable from the exact solution. Okay, but what we've used here right now, the solve function, is actually a direct solver. And we want something that scales like O of n, if we can get it. That was our entire idea behind doing this. So exactly like with molecular dynamics, when you have these small problems like the ones I'm showing you now with N17, of course, it makes absolutely no sense to invest so much work into your solver but when you have n equals 10 to the power of 6, then the terms in this solve here will kill you. So the n to the power of 3/2 is just going to be too much, and you'll spend days and days and days calculating your solution when you could just spend a few hours. So that's the reason why we're doing this, even if it's not always immediately obvious from the examples that I chose here, which have very small n's. But otherwise I couldn't just do this in an IPython notebook. Okay, so that's our motivation for where we want to go. We want to replace the solve with the smoother. And as we saw last week, the smoother converges very, very, very slowly for this problem. So that brings us to multigrid. Our observation was that the high frequency error is relative to the mesh size. So what we want to do is we want to create a hierarchy of meshes and then reduce the high frequency error on each of them. But what's high frequency on a very coarse grid is low frequency on the finest grid. So then we can then we can effectively reduce all frequencies of errors if we have enough grids. So we use multiple grids to solve the system of equations, and we hope that on each grid a certain range of error frequency will be reduced efficiently, and that we cover all different error frequencies this way. So let's start with something that's called a nested iteration. So this will be comparably to the pure smoother, very fast. It can give us a good initial guess, and is sometimes referred to as a poor man's multigrid. It's not a full multigrid yet, but it uses all the ideas. So let's have a look at that to start with. Okay, so we start on a very coarse grid. I don't know why it's not rendering my LaTeX here, but okay. We start on a very coarse grid with a mesh size of, let's just call it H0. We guess some initial solution, so again we can just put zeros as we have before. Then we iterate to solve this using some smoother, giving us an approximate solution on this very coarse grid. Now we interpolate the solution to a finer grid with a mesh with H half, so we just double the number of mesh points roughly. And then we proceed to step 2 again, only now we use the solution that we got from the coarser grid as our starting point for our relaxation method. Okay, so let's see if that works. Let's recall the Gauss-Seidel smoother, so we'll use Gauss-Seidel here, although you could use, in principle, other smoothers as well. But this matrix is not diagonally dominant, so you can't use Jacobi. Be careful with that. We're going to use Gauss-Seidel. So this is just exactly the same code as we had last week, and which I explained last week. It's basically getting a matrix that we want to solve for, a right-hand side B, an initial guess x0, and a maximum number of iterations. Okay, so then let's do a nested iteration. So first let's get the approximation on the coarse grid. So we'll use this n equals 5 as our coarse grid. We could also use n equals 3, but I think that's really, really bad. Yeah, so that's just one basis function approximating this. So let's stick with 5 as our coarsest grid, which gives us something which sort of looks like a solution at least. So we set up our stiffness matrix corresponding to that. We set up our right-hand side corresponding to that. And now we can compute the coarse solution using a Gauss-Seidel method. In orange, again, is the actual exact solution which we know in this case. If we use 10 iterations, because this is a very small matrix, the solution looks really good. But if we use just 1, for example, then the solution is still complete nonsense, right? Let's see, 3 is not enough. 5 is also not enough. Let's stick with 10. Okay, so that's our first grid. So now we've got this solution, and we need to somehow move over to the finer grid with more grid points. So we need to interpolate the solution onto the fine grid somehow, because it currently doesn't live there. So for this, we're going to use an interpolate function, which I'll talk about in more detail later. So for now, I'm not showing you the actual function. I'll just tell you it exists. So what does it do? I hate that it doesn't scroll down. Okay, so here is your course grid solution. It has basically values at these 5 points that you can see quite clearly here. And our fine grid also has to be evaluated here, 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 and here. And now the interpolation is given by these orange points. So as you can see, we've just chosen the value that it has here. And how you do that, as I said, we'll discuss later. So now we have a starting guess for our next iteration. Let's see what happens if we do that. So now we've doubled the mesh width. So we've gone from h equals 0.25 to 0.125. We can create a new stiffness matrix. We can create a new right-hand side corresponding to that n. And now we can try to solve using Gauss-Seidel. So first, let's do what we did last week. We will give it just zeros as an initial guess. And then we'll do 10 iterations. Okay, so now our solution is really bad, right? So this is much, much smaller than the true solution. And you can also see that there's still very low frequency errors here. So errors that span the entire domain. So what happens if we choose the starting guess as being the coarse solution interpolated onto the fine grid? So this is just using the interpolate. And now we're using this as an initial guess for our iteration. Well, then we get a really good approximation already. And that was basically the entire idea. We can now do this iteratively. So instead of just doing it for 2 grids, we just continue and continue, refining and refining. And in each case, once we've solved on that grid, we interpolate the function, and then we use that as a starting guess for our Gauss-Seidel relaxation in the next step. But if you choose fewer iterations here, you already start to see one of the problems, namely that the error here isn't a high frequency error. The difference between these two here is a low frequency error. There's errors which are spanning the entire domain. And there's ways to fix that. So let's look at those. So we come to the multigrid idea, or rather the second idea, because the first multigrid idea was to create this hierarchy and then to use these as initial guesses. So what we've observed here is that the error in the interpolated initial guess still includes low frequencies. And the coarse mesh was just there to remove those low frequencies. So we've reduced them, but we haven't gotten rid of them. That means that the relaxation is still slow. So the question is can we go back to a coarser grid later in the algorithm? And right now we can't, because we don't know how to do that. But of course, actually we can. So here again, we're going to use the residual equation. You're quite used to the residual equation now. We use that extensively when we were doing the smoothers in the first place. So instead of solving the linear system itself, we solve for error terms, and then we always correct our solution using these error terms. And add that approximation to the fine grid solution. So basically on the coarse grid, we're going to compute something like this, and then we're going to use that to correct the fine grid solution. Okay, and now this is our new 2-grid method. We start by doing smoothing on the fine level. This leads to an approximate solution. So we're not going to do hundreds or thousands of steps here. We're just going to do I don't know, 2 or 3 is quite normal, just some pre-smoothing. Then we compute the first residual. We restrict the residual to our coarse grid. So here the coarse grid has a mesh H. In this case, this is just 2H, so we've just halved the grid for the fine solution. Then we compute a coarse grid solution. And here, when we apply the smoother, we actually continue on until we get convergence. Then we interpolate this coarse grid solution error to the fine grid and added the correction to our solution. And then we do some more smoothing steps on the fine grid. And then we can continue doing this until we've converged. Okay, so this had a bunch of components, but most of them we've actually already covered. So the smoother reduces the high frequency error components on each of the grids. That we've covered extensively. There needs to be a restriction. So there needs to be some way of transferring a residual from a fine grid to a coarse grid. We'll discuss that later. We need a coarse grid equation. So we need some discretization of the PDE on our coarse grid. So right now we've been doing that by just discretizing again. There's other ways of approaching this that we'll also look at later. Actually, we'll look at those next week, not this week. And then there's the interpolation. We've already kind of seen what effect it has, but we haven't seen how to compute it. So so that's just saying this again. We have the following components. We have the smoother, we have the coarse grid equation, but we're still missing the interpolation and the restriction. Okay, so the interpolation takes a coarse grid solution and transfers it to the fine grid. So if we're transferring from a grid with mesh width h to a grid with mesh width h half, then we're missing a value for every second coefficient. It basically has twice as many nodal values that we need to have, and we don't have them. So here again is this example. So we have values at 5 points, but we need them at 9 points. And the question becomes, how do we find these? So interpolation, I should probably point this out, is also called prolongation sometimes. So if you're reading this in a textbook and you see prolongation instead of interpolation, then that's why. It's usually denoted either with an I or a P for this reason. And we now have a bunch of different options for this. So as so many things in this course, there's not one true answer to this. It depends a lot on the problem that you want to solve. What you should choose is an interpolation. So the very easiest thing that you might think of doing is to just assume that the value that something has at a certain nodal point is just the same if you move slightly to the left or to the right of it. So then you just choose that value to interpolate with. But that usually gives us a too large approximation error. I don't know why I wrote small there. So it leads to a too large approximation error. Otherwise, we wouldn't mind. So that's not a good approximation. If you look again at this picture here, then that would basically mean that this point here would also be at 0, and this point here would be down here as well. And that's obviously not such a great approximation in this case. In some situations, though, it gets used, so cell-based coarsening. So finite volume methods, for example, always approximate the function as a piecewise constant in each cell. And in that case, of course, this is a great way of doing interpolation. But right now, we have piecewise linear basis functions, and we can't do this. So the next option would be to go to higher order polynomial interpolation. So we could do a quadratic interpolation or a cubic interpolation. In practice, that's usually too costly. You can do more smoothing steps instead, and then you get rid of the disadvantage of lower order interpolation. So that's always going to be the better option. So what does that mean? It means that when we look at this, now we could also assume that there's a quadratic lying through this, and then this point would actually end up somewhere around here, which is a slightly better interpolation. if you remember what the true solution looks like. It's closer to that. But it would also be pretty costly to compute, because we'd need to actually set up the quadratic polynomial interpolant, and then compute that. So in practice, we're not going to do that. Instead, we're going to do a piecewise linear approximation, which is quite reasonable considering the fact that we have linear basis functions. Okay, so what does that look like in matrix form? It's basically just ones in all the locations where the grid points exist. So every second grid point, it already exists on the coarse grid, so we just transfer directly. So this is the coarse grid, and the fine grid also contains x1, x2, x3. And in between those points, we need to do something else. So we just half each of the points to the left and the right of it. So here there's zeros. Those zeros are just the nodal points where we have Dirichlet boundary. And again, notation-wise, you'd either use this I for interpolation or P for prolongation. Yeah, that's how you'd write this. Okay, so let's now have a look at what the function actually looks like. So this is exactly the plot we saw before, but now I've put the function that's actually computing this in there as well. So we take a coarse solution, which is here called U coarse, and we want to compute our fine solution, U fine. And so I just initialized it with a vector of zeros. That's just for convenience. And now all the even valued parts of the fine solution can just be taken directly from the coarse. So that's exactly the ones written here. So x1, x2, x3. And then the odd ones need to be computed. So now they're 1/2 of U coarse plus at I plus I plus 1. Okay, and then that gives us this picture. So this is just a way of multiplying out that matrix vector product without actually setting up the matrix. But you can also do this directly by actually setting up the matrix given here and then computing this matrix vector product. In this case, though, it's more efficient if you just directly set up this vector, as I've done it here. So let's look at a problem where the linear interpolation is not a good idea. We'll have a look at the convection diffusion equation. So far as a test or toy example, we've used the Poisson equation. The convection diffusion equation isn't a lot more complicated than the Poisson equation. In fact, the first part here is just the double derivative of u again. So it's again just the Poisson equation, only now multiplied with some factor epsilon, which we're here going to assume is very, very small. And then we have a second term which only has a single derivative on it that we're adding with this, which is also multiplied with some constant, which here is going to be c. And then we have our right-hand side vector f again, only in this case we're just going to assume that we have the homogeneous problem, so we're going to assume that the right-hand side f is equal to 0. And we'll again assume Dirichlet boundaries, only in this case they're not 0 Dirichlet boundaries. So at the left boundary we'll assume that the solution is 1, and at the right boundary we will assume that it's 0. And this has the advantage that for this case we can just directly compute the exact solution, and then in the following slide we can exactly see what should be happening and why the linear interpolation is not a good idea. So on the whiteboard, let's go see why u of x is the exact solution to this problem. Okay, so now let's just see that the solution is correct. So as on the slide, we think that the solution looks like this. So it's just some exponential terms. And we are claiming that it is a solution for the following PDE. where you've got double derivatives and a single derivative with an epsilon and a c. Okay, and u of 0 and the following boundary conditions. So u of 1 should be 0 and u of 0 should actually be 1. Okay, so that's the equation that we want to solve. So let's just see first whether the boundary conditions hold. So u of 0. So that's 1 minus 1 e to the power of c divided by epsilon, and then here we get e to the power of 0 minus e to the power of c divided by epsilon, and this is clearly 1, so then these two cancel out and we get 1. So that's great. And we can look at the other interval endpoint. So here we have 1 minus e to the power of c divided by epsilon, and then we have e to the power of c divided by epsilon minus e to the power of c divided by epsilon is equal to 0. Okay, so both of our boundary conditions already hold. Now we need to see that the equation itself holds. And for that we need to derive u of x. So dx u of x, let's derive it once. 1 minus e to the power of c divided by epsilon. So this term is just constant, and this term is obviously not constant, so then we get a c divided by epsilon e to the power of cx divided by epsilon. Okay, so that was the first derivative, and now we can compute the second derivative as well. And now this is c divided by epsilon squared, because we get in the second one when we derive this a second time, and the exponential still remains unchanged. Okay, and now we just need to see that when we multiply this with the first one with epsilon and the second one with c, that we get 0. So minus epsilon, I'll write all of them out. 1 minus e to the power of c epsilon, c divided by epsilon squared, e to the power of cx divided by epsilon. That's the first term, plus c times 1 divided by 1 minus e c epsilon. And then this term, so c divided by epsilon, and then e to the power of cx divided by epsilon is equal to 0. Okay, so we can first start by multiplying with 1 minus e to the power of c divided by epsilon to get rid of these two terms. And then we can simplify here, so then we get c squared divided by epsilon, minus sign here, and the term ecx divided by epsilon. And then we can look at this term, well, c times c squared, and then just a single epsilon divided by epsilon, and then this term, e to the power of cx divided by epsilon, and now these two cancel out perfectly, so we get 0. Okay, so this is clearly a solution to our equation, and we can